Let us now focus our attention on the electrons in an atom. And the first question is this: why should we focus our attention on the electrons? The reason is because in chemistry, electrons are the only subatomic particles that participate in chemical reactions. Neutrons and protons do not participate in ordinary chemical reactions. What do I mean? In chemistry, electrons can be transferred from one atom to another, or electrons can be shared between two atoms. We will learn about these two types of chemical activities. But for now, let us remind ourselves what we know so far about an atom. According to Ernest Rutherford, an atom has a nucleus. Inside the nucleus, we have the protons and the neutrons. And the electrons are distributed outside the nucleus. This is the question: how are the electrons actually distributed? The best answer to that question is found in quantum chemistry. But let us just introduce ourselves to the concept of electronic arrangements in atoms. Beginning from the Rutherford's model of an atom, a physicist named Niels Bohr proposed a model for an atom. You must have seen that model of an atom before. It looks like this. Let us assume this is the nucleus of the atom. According to Niels Bohr, the electrons in the atom are arranged in shells around the nucleus. The shell closest to the nucleus is labeled as the K shell, or at times it is called N equals to 1 shell, where N means energy level. The second shell to the nucleus is labeled as the L shell, or N equals to 2 energy level. The third shell relative to the nucleus is labeled as the M shell, or N equals to 3 energy level. And the next after that is labeled as N shell. They are labeled alphabetically, or N equals to 4 energy level. There are more shells, but let us stop on N equals to 4 for now. Each shell can only hold a certain number of electrons, and there is a very simple formula for calculating how many electrons can be found in each energy level. The formula is given as 2n squared. So this is the formula for finding the maximum number of electrons in the energy level of an atom. Let us quickly calculate how many electrons we can find in each energy level. Let us begin with energy level number 1. If n is equal to 1, if you plug 1 into this equation, then you are going to get 2 times 1 square. 1 square is equal to 1 times 2 gives you 2. What that tells you is that the K shell of an atom can only hold a maximum of 2 electrons. You can never find more than 2 electrons in the K shell. If n is equal to 2, plug 2 into the equation and you have 2 multiplied by 2 square, which gives you 8. What that means is that the L shell, or n is equal to 2 energy level, can only hold a maximum of 8 electrons. You cannot have more than that in the L shell. When n is equal to 3, you have 2 multiplied by 3 square, and that is going to work out to 18. What that means is that the M shell can hold a maximum of 18 electrons. But the N shell is now getting rather big, and it is actually splitted into 3 subshells. So, subshells of M. The first subshell can hold a maximum of 8 electrons. The second subshell can hold a maximum of 8 electrons, and the third subshell can hold a maximum of 2 electrons. Based on this little rudimentary understanding of electronic distribution, let us now try to understand how the electrons in the atom of each element are distributed. Let us begin with hydrogen. Hydrogen is element number 1, which means it has 1 proton and 1 electron. The only electron in hydrogen will move to the lowest energy level possible, and that will be the K shell. So, if we are to draw a visual representation of it, the single electron in hydrogen will be in that shell. The other shells will be empty. Let us take a look at helium. Helium is element number 2, which means it has 2 protons and 2 electrons. Let us try to draw a visual representation of that. If this is the nucleus, the K shell, remember, can hold a maximum of 2 electrons. So, both electrons in helium can be accommodated in the K shell. The next element is lithium. Now, lithium has 3 electrons. The first 2 electrons in lithium will move into the K shell. Now the K shell is completely filled. But the remaining 1 electron will move into the L shell. The next element is beryllium. Beryllium has 4 protons, and that means 4 electrons. The first 2 electrons will move into the K shell. The remaining 2 electrons in beryllium will move into the L shell. Let us take a look at boron. Boron has 5 electrons. The first 2 electrons will be accommodated in the K shell. The remaining 3 electrons will be in the L shell. Let us take a look at carbon. Carbon has 6 electrons. The first 2 electrons in carbon will be accommodated in the K shell. The remaining 4 electrons will be accommodated in the L shell. A quick reminder, the L shell can accommodate a maximum of 8 electrons. Let us quickly jump to neon. Neon has 10 electrons. The first 2 electrons in neon will be in the K shell. The remaining 8 electrons can be accommodated in the L shell. Now the L shell is completely filled. Let us now move on to sodium. Sodium has 11 electrons. The first 2 electrons in sodium can be found in the K shell. The next 8 electrons can be found in the L shell. The remaining 1 electron can be found in the first subshell of the M. Remember, M shell has 3 subshells. So the remaining 1 electron will be in the subshell of M. Let us take a look at a very quick electron arrangement for the first 20 elements. So elements from hydrogen down to calcium. These are their symbols, and these are the number of protons in the nucleus of each of them, also called the atomic number. This is the K shell. This is the L shell. This is the first subshell of M, and this will be the second subshell of M. Hydrogen has only 1 electron, and that single electron is in the K shell. Helium has only 2 electrons. Both electrons can be accommodated in the K shell. Lithium will be 2 in K, 1 in L. Beryllium, 2 in K shell, 2 in L shell. Boron, 2 in the K shell, 3 in the L shell. Carbon, 2, 4. Nitrogen, 2, 5. Oxygen, 2, 6. Fluorine, 2, 7. Neon, 2, 8. And now The L shell is completely filled when we got to neon. Let us now move on. Sodium has 11 electrons. So how will they be arranged? 2 of them in the K shell, 8 of them in the L shell, the remaining 1 in the first subshell of M. Magnesium has 12 electrons, so it will be 2 in the K shell, 8 in the L shell, the remaining 2 in the first subshell of M. But also remember, the first subshell of M can only take a maximum of 8 electrons. So as you fill in the electrons, always remember that. So aluminum would be 283, silicon will be 284, phosphorus will be 285, sulfur 286, chlorine 287, and argon 288. Now, the first subshell of M is completely filled. If you now move on to potassium, potassium has 19 electrons, the first 2 of which will go into the K shell. The next 8 will go into the L shell. Another 8 will go into the first subshell of M, and the remaining 1 will go into the second subshell of M. And you get the idea for calcium. Now, why are we looking at all of this? This is the first reason. Take a look at helium, neon, and argon. Those 3 elements. If you look at each of them carefully, you will see that all of their shells are completely filled. Helium has only 1 shell, the K shell, and the K shell is completely filled. Neon has 2 shells, K and L. Both of them are completely filled. Argon has 3 shells. The 3 of them are completely filled. That is why they do not participate in chemical reactions. They do not want to give out electrons. They do not want to take in electrons. And they do not really want to share electrons. And that is why they are called noble gases. So, helium is a noble gas. Neon is a noble gas. Argon is a noble gas, which means that they are very stable. They do not really want to react with anything. And remember, all the other elements would want to be as stable as they are. Another thing I need you to quickly take a look at in the electronic arrangement we have here is the number of electrons in the outermost shell. This is what I'm talking about. Take a look at hydrogen. Only 1 electron in its outermost shell. Take a look at lithium. Only 1 electron in its outermost shell. Take a look at sodium. Only 1 electron in its outermost shell. And take a look at potassium. Only 1 electron in its outermost shell. What is common to these 4 elements? Take a look at the periodic table. You will see that they all belong to the same group, group 1A. That 1A is an indication that they all have the same number of electrons in their outermost shell. And we have a name for the number of electrons in the outermost shell of an atom. It is called valence. So what is the valence of beryllium? Beryllium is in group 2A, which means it has 2 electrons in its outermost shell. So is magnesium, calcium, strontium, barium, and radium. They all belong in the same group because they all have the same number of electrons in their outermost shell. And again, you can confirm in the electron arrangement that we have here. Beryllium, 2 electrons in the outermost shell. Magnesium, 2 electrons in the outermost shell. Calcium, 2 electrons in the outermost shell. So that is telling you that elements that are in the same group will react in similar ways. Elements in the same group will react in similar manner. The reason is because they have the same number of valence electrons, which means boron, aluminum, gallium, indium, thallium, and nihonium will all have 3 electrons in their valence because they belong to group 3A, and they will have similar chemical reactions. And the same thing goes for all the other groups. The next question to ask is then, how will each of these elements react in a chemical reaction? And the answer to this question is rooted in how the electrons are arranged. To understand this, let us begin with lithium. Lithium has only 1 electron in its valence. That electron is in the L shell. The L shell can accommodate 8 electrons. Now remember, each element wants to be like a noble gas. So how can lithium be like a noble gas? The nearest noble gases to lithium are helium and neon. To be like helium, lithium would have to lose the only electron it has in the L shell. To be like neon, lithium would have to gain 7 electrons into the L shell. The lowest energy pathway for nature is for lithium to lose the only electron in its L shell. And when lithium loses that single electron, lithium will carry a charge of +1. Let us take a look at beryllium. Beryllium has 2 electrons in the L shell. There are 2 pathways for it to be like a noble gas. It can lose the 2 electrons that it has in the L shell, or it can try to find 6 electrons to be like neon. The easiest would be for it to lose the 2 electrons, and that is the pathway that nature usually takes. So beryllium, after losing 2 electrons, will carry a charge of +2. Boron also has 2 possible pathways. Lose the 3 electrons in the outermost shell to be like helium, or gain 5 electrons to be like neon. Nature would always go via the easiest pathway. So boron will end up losing 3 electrons and having a charge of +3. Carbon is in a unique position. Carbon has 4 electrons in its valence. So, which pathway is more suitable? Should it lose the 4 electrons to be like helium, or gain 4 more electrons to be like neon? There is no pathway that is more favorable than the other. And because of that, carbon can have a charge of +4 or -4. The next element is nitrogen. Nitrogen has 5 electrons in its outermost shell. 2 pathways are possible to be like a noble gas. Gain 3 electrons to be like neon, or lose all the 5 electrons. Losing the 5 electrons would cost too much energy. So nature usually ends up gaining 3 electrons for nitrogen. And that is why nitrogen is going to carry a charge of -3. Oxygen would have 2 pathways: gain 2 electrons or lose all the 6 valence electrons. Oxygen is going to have a charge of -2. Fluorine has 7 electrons in its valence. Gain 1 electron to be like neon, or lose all the 7 electrons to be like helium. Obviously, the easiest pathway is for fluorine to gain 1 electron, and it will carry a charge of -1. Let us now take a look at the periodic table. This is the summary of what we have learned so far. Lithium is going to carry a charge of +1. And so will all the elements in group 1A. Beryllium is going to have a charge of +2. And so will all the elements in group 2A. Boron is going to have a charge of +3. And again, all the elements in group 3A will end up having a charge of +3. Carbon is in group 4A. It can be +4 or -4. Nitrogen is from group 5A. Every element in group 5A is going to have a charge of -3 when they react in a chemical reaction. Oxygen is from group 6A. Every element in group 6A will end up having a charge of -2. Fluorine is from group 7A. Every element in group 7A will end up having a charge of -1. And group 8A are the noble gases. They do not like to react.